Hello, my name is Christopher Banks, and today I will be presenting to you my work in CS 7641. As a group project, we worked on anomaly detection in AUV images. A lab at Georgia Tech has developed the underwater robot Icefin to explore the oceans beneath glaciers in Antarctica. On its dives, it collects video from a forward-facing camera. This results in large video files, however, which makes hunting through the video to pick out interesting features time-consuming. Additionally, these videos could be used live to have the robot find interesting features itself and autonomously decide to investigate them. So this introduces the need for anomaly detection, which means finding an interesting feature in a set of camera images. The Icefin these are the specifications of the Icefin. Has a maximum diving depth of over 1 kilometer. It weighs 130 kilograms. It's 3.5 meters in length, and it has a communication range of 3.5 kilometers. Its instrumentation includes, but is not limited to, HD cameras, sonar systems, Doppler current profiling, and salinity and temperature measurement devices, as well as many other instruments needed to analyze the ocean and the ocean floor. However, when analyzing the video data, we see that most of the video data is sparse, meaning that there could be hours and hours of video data collected where there's nothing but empty ocean for the robot to record. Once this robot has recorded this video data, however, researchers will have to comb through these hours and hours of video data in order to determine anything that's useful for further analysis. So what kinds of anomalies are we interested in looking at? So these are some of the anomalies that Icefin will likely encounter, such as seafloor life, like the coral reef or anemone, or interesting ice structures like this glacier crevasse or the ice sheet. All of these would be important to recognize, but some, such as the glacier crevasse, might be more interesting to investigate. Therefore, we'd like to both identify camera images that have anomalies and then learn how to differentiate anomalies from each other. So this brings us to our questions. How do we identify significant data versus empty data? And two, is there a way to autonomously classify objects encountered by Icefin? So our solution is a two-stage classification architecture, which involves a supervised learning approach, where we develop a convolutional neural network, and an unsupervised learning approach, where we develop and compare k-means and Gaussian mixture models. For the supervised learning portion of our project, we decided to use a convolutional neural network, or CNN for short, to classify the images between those with anomalies and those without. The first step in developing the CNN was to pre-process the images. We normalized the RGB values and used data augmentation because our data set consisted of 2,000 images. We modeled our CNN after the popular VGGNet and decided to split our data set between 80% training and 20% testing. After training our CNN model on 10 epochs and then 32 epochs, we found that the final accuracy exceeded 99% for both trials and did not show signs of overfitting. Our metrics included accuracy and a binary cross-entropy loss function, or the log loss function, shown here for completion. As you can see here from the plots, we show that for the 10 epochs, it levels out for both the training accuracy and the testing loss, training and testing loss functions around the 10 epoch level. For the 32 epochs, the accuracy and loss values steadily increase and decrease respectively, but begin to plateau after 10 epochs. This tells us that the ideal accuracy and loss could be achieved with only 15 to 20 epochs. We further visualize the results by having the model classify 6 sample images, which can be seen below. The model was able to classify all of the sample images correctly, where you can see that for the non-anomaly images, we show empty ocean space, and for the anomaly images, the classification algorithm detects that there's something worth further investigation. And this is for the 32 epoch result. In addition to classifying labeled data as anomaly and non-anomaly types, we are also interested in grouping anomalies with similar features. We utilize the unsupervised learning techniques k-means and Gaussian mixture models to group images of similar anomalies. Using these clustering techniques, we're able to group data using 2 different models. The non-parametric k-means, which assumes a circular clustering of data, and the parametric Gaussian mixture models, or GMMs, which assumes the total data is a linear combination of clusters modeled as normal distributions. In addition to this, we use the evaluation metrics of the silhouette coefficient, which is the measure of the intra-cluster distance for clusters, where generally the higher the better, and the Davies-Bulgin score, which is a measure of the ratio of the intra-cluster distance versus the inter-cluster distance, where generally the lower the score, the better, followed by the root mean squared error for the k-means. The feature space we chose for k-means was the RGB histogram of an image, which we transformed by a principal component analysis, or PCA. 2 important studies were done to determine the parameters for the feature space. First, the number of clusters for which the root mean squared error was calculated for the results with varying numbers of clusters. The choice of k falls in the elbow of the plot, which is approximately 9 to 12. And then next, we investigated the number of PCA components needed to cluster the images by calculating the root mean squared error for a varying number of components, and chose a number of components close to the steady state value. For our results for k-means, we see that we got a Davies-Bulgin score of 0.76 and a silhouette coefficient of 0.55. But what's more telling is looking at the clusters themselves. For some anomalies, the algorithm could successfully cluster features regardless of the placement in the image or lighting. However, some other clusters results, which were more based on the lighting of the picture than the object, causing somewhat similar anomalies to be grouped together. So then we move on to see if Gaussian mixture modeling in the dataset could resolve these issues. Using the Davies-Bulgin score index for quantitative metrics, defining how well the clusters are separated, we get a value of 0.62. And while a lower score is usually desirable, the high dimensionality of the feature space may have had an effect on the separability of the data in addition to the choice of the feature space. We'd like to note that for our feature space, we used a histogram of oriented gradients in the HSV values of each image. We then combined both these sets of features as the feature vector for one image. Afterwards, we applied PCA with 5 components to reduce the total dataset used. And in addition, in order to find the best model, we used Bayesian information criterion to find the best model for our data. And for this dataset, the best model had 9 components, which you can see in this graphic to the right, where the best model is indicated with the star above it. So looking at the GMM image results, we see that we get the Davies-Bulgin score of 0.62 and a silhouette coefficient of 0.628, where a score closer to 1 indicates better separation in the clusters. Qualitatively, we found the algorithm does a reasonable job at finding similar objects and grouping them, particularly with some images of the coral and the seafloor. However, we found that the camera positioning can have an effect on accurate clustering of images, suggesting that the clustering we do is not invariant to all scaling or rotation transformations. So in conclusion, the results of the CNN are very promising for future use. With only a small dataset, the model was able to classify images with near perfect accuracy. Similarly, the results of clustering are promising, but may require additional work to be done to achieve better results, including semi-supervised learning for anomalous objects would be an interesting next step and could resolve some of the current issues with clustering. With the results of the unsupervised learning clustering algorithms, it seems very possible to use both systems in practice. Thank you for your time, and if you have any questions, I would be happy to answer them.